Hello, this is Paul from Foresight Tech. In this video, we are going to deal with the derivatives of inverse trig functions. Our focus is on the proofs of the derivative formulas for all 6 types of inverse trig functions using implicit differentiation we learned from the last topic. Let's see the material. And first, I will introduce the derivative formulas one by one and give a proof as well. Then I will summarize all the derivative formulas together, which will help you memorize them. Last, we will practice 2 questions together about how to use the derivative formulas. And here is the first formula. So can we see? Okay, so we were going to deal with the inverse sine function, right? That's the inverse sine, or you can say is the arc sine. Let me write another notation. So sometimes you use inverse sine, okay? Sometimes you use this arc sine. They are the same, right? They are the same. We learned this from trigonometry. And the formula is 1 over square root of 1 minus x squared. Okay, and our major focus is how to prove this. And we have 6 types of inverse trig. Okay, each type we use the same method. We call it implicit differentiation. And let me highlight this. This is the most important one. Okay, so we are going to use this implicit differentiation we learned from the last topic, okay, to prove all the formulas in this video. And I will take a little bit more time to the first formula, okay, and then all the other formula will follow the same method. I will go much faster than the first one. Okay, so how to do now? And we said we need to use the implicit. So how to use the implicit? We need to get the implicit equation, right? So the implicit equation is just comes from the definition. Okay, what is the definition? Let me show. Here is the definition. Okay, the definition is here. Let me highlight it. What does it mean? The inverse sine, which means y is the angle, right? We need to find, and the sine at this y at the angle equals x. This is the implicit equation we have. Okay, sine y equals x, but y is the angle. Where is the angle? That's the most important. The angle is between. See, y is between negative pi over 2 to pi over 2, which means the quadrant 1 and the quadrant 4, right? Okay, so now from here, we're going to this implicit equation. We need to find the derivative of y to x, right? Which means implicit equation, we need to do the implicit differentiation. So we have to differentiate both sides of this equation, right? That's all we learned from the last topic. Let me highlight. Okay, so we found here is the equation. Implicit equation. Let me write. This is the implicit equation we are going to use. Okay, and the implicit differentiation, which means we have to do this. Differentiate, right? Both sides of the equation. Both sides of this implicit equation. And let me see. Okay, we take a derivative to the left, take a derivative to the right. Okay, to the right is easy, is 1, right? Take a derivative to the left. What do we do for this term? Of course, this is a composite function. The outer function is sine. The inner function u equals y, because y is a function of x, right? Okay, so you know how to do. We have to do this. Use sorry. Okay, so we have to do what? We have to use the chain rule. This is a composite functions. How to do chain rule? The most popular, the most important tool for us, right? Okay, the chain rule give us we need to find the derivative of the outer, derivative of the inner. What is derivative of the outer? Sine y or sine u is the outer, right? Sine function is the outer. Take a derivative goes to cosine. Of course, cosine y. And the inner is dy dx. Y take a derivative because the inner is y. That doesn't make sense. Okay, this is the most important. Okay, we have the left. The right is 1. Now, what do you do? Solve this equation, right? What do we need? We need the dy dx. Okay, we solve dy dx. We solve for dy dx. Therefore, what do we get? We get dy dx is 1 over cosine at y. Almost, right? We get this. But we need the what? We need to back substitute. Okay, so we need to get x. How do from y to x? Okay, and if we look back, x is sine y. Okay, x is sine y. But here is not a sine y. Here is a cosine y. We can make a cosine y to sine y. What is the link? The Pythagorean, right? The most famous trig identity we learned before. Let me show here. Pythagorean. Okay, and this step we're going to link a cosine to sine. Pythagorean. Which Pythagorean? The first. Cosine square plus sine square. Remember, equals 1. Can you see? Cosine, we can go to sine, which is the square root of 1 minus sine. But we have a sine, either positive or negative. What is cosine? And in this case, okay, cosine is positive. Why cosine is positive? Let me look at y. See, here is the most important. Y, it belongs to Q1, quadrant 1, and quadrant 4. No matter which quadrant, cosine always positive, right? Okay, so that's why we don't have a negative here on the bottom. Okay, it's good. The last step, is easy because we have sine y is x, right? Okay, well, directly put here. Because sine y is x. So we plug sine y by x. Therefore, we get the final 1 over square root of 1 minus x squared. Here is the final. That's the proof, okay, for the inverse sine. We can summarize a little. So look, it's not difficult, okay. All we need is implicit differentiation. And also pay attention to this chain rule. And another is the trig identity. Okay, we learned that from trigonometry a long time ago. Now let's look at the second. All the other 5 types are very similar. Okay, so I will go much faster. So can you see the inverse cosine take a derivative? Very similar, but we do have a negative at the beginning. Okay, why? Pay attention to this negative. And of course, we do implicit differentiation, and we will use the implicit equation, which is the definition. Can you see? Let me highlight one more. So here is the where y belongs. Y belongs to 0 to pi. Excuse me, which is different from sine, right? Inverse sine. Then now, what do we do? Okay, do the same. We do the same. Okay, we look at this definition: cosine y equals x. Okay, and we need to. This is implicit equation. We need to differentiate both sides. Okay, we need to differentiate both sides of this implicit equation. The same, okay, as we did from the last. Okay, let me see. So take a derivative to the left, take a derivative to the right. We say the right is 1, right? So what the left now is the same. What is the left? Let me highlight this because y is a function of x, therefore y is the inner. Okay, so we have to use the chain rule again. Can you see? All the steps are the same. Chain rule to this. Okay, so chain rule was the outer function. Cosine take a derivative is negative sine. Can you see? this negative, where that negative in the formula came from here, okay? And then this is the inner, okay? So far we get it to this step. Now the same, we solve for dy dx. What do we get? We get a negative 1 over sine y. How do you change sine to cosine? Of course, Pythagorean. Then now it's the same, right? Pythagorean we use. Let me just show you here one more time. And the sine y is no, sorry. So I will not use this. I will put the original Pythagorean. Okay, so you can see the detail. Okay, because sine square plus cosine square equals 1. This is the Pythagorean we used, okay? So we can solve for sine, which is a square root of 1 minus cosine square. However, we have positive or negative. Can we look at it? In here, sine is still positive, okay? Sine y still positive. So we don't have a negative. Y sine is a positive. Can we look at the y? Y belongs to 0 to pi, quadrant 1 or quadrant 2. For sine, always a positive, right? See, that's y. Sine is positive, therefore we get to here. The last you know is what? It's just put back the definition, because cosine y is x. Okay, therefore we have the formula at the end. This is the proof for the second, very similar, right? Now, we look at the third type, which is inverse tangent, okay? Inverse tangent, can we see what the difference? Almost no difference, okay? So can we see at least the method are the same? We're going to implicit differentiation. Let me highlight the one, okay? So tangent y equals x, of course, this is the implicit equation, right? And where is y? Pay attention to this. Y is negative pi over 2 to pi over 2. Okay, so that's the definition. Which means y still belongs to Q1 and the Q4, right? Q1 or Q4. Okay, now what do we do? The same. All the methods are the same. So I hope you get it. So I put it here. This is the implicit equation. What do? We differentiate both sides, okay? We take a derivative to both sides, which means differentiate both sides and see what do we get. We get this. Okay, we get the left take a derivative, the right take a derivative. The right is still 1, but the left is still chain rule, right? Okay, let me see. Here, still chain rule. You know, because what? Because y is a function of x, right? Because y is the inner, y is a function of x. That's chain rule again. Okay, if we use the chain rule, can you see? We have the derivative of the outer 10 times derivative of the inner. This is the inner, right? Derivative of the outer is what? Tangent take a derivative, which is secant square. This is the derivative of the outer, and therefore easily to get this equation. Now what do? Solve for dy dx, and then we get 1 over secant square, right? Okay, so in our question is tangent y equals x. How do you change it to secant to tangent? Of course, another Pythagorean. So it's here already. Secant square is 1 plus tangent square. Do you remember this Pythagorean? Okay, we have 3 type of Pythagorean we learned them from trigonometry. Did the second, okay? So let me see. It is a Pythagorean, okay? Identity. Now the last, of course, is easy because tangent y is x, right? And from the beginning of these questions, tangent y is x. That's the definition. Can you see? Tangent y is x. Okay, or we look back a little. Tangent y is x. Therefore, we plug back. Okay. So what do we get? This is the answer. And we finally have the formula, which is a tangent inverse tangent take a derivative is 1 over 1 plus x squared. And now we look at the fourth one. Still the same. Okay, so I hope you have all the idea. And one more. Can you see here we have a negative this time? If we take a derivative to the inverse cotangent, and very similar with the inverse tangent, but we do have a negative here. Please pay attention to why we get a negative. The method is the same. Okay, so what do we do? And we use this implicit equation, which is the definition. Cotangent at y equals x. Okay, where is y? Y is belongs to 0 to pi, so don't forget this. And y belongs to 0 to pi, which is important. Now we have the implicit equation, take a derivative, right, to both sides. Let me see. Here, of course, is easy. We just differentiate both sides. Differentiate both sides. Okay. And see what do we get. Of course, we get very similar. The left take a derivative. The right take a derivative is 1. The left take a derivative is chain rule again, right? Is this chain rule? Because y is a function of x. Okay. So here what do we get is chain rule again. Okay. And if we find that the outer function, can you see? The outer function is cotangent at u, which is cotangent at y. Take cotangent, take a derivative is negative cosecant square, right? Can you see? Here is where we get the negative. The inner is y take a derivative to x, of course, and then the right side equals 1. Can you see? Almost right. We solve this equation for dy dx, and we will get the answer. If we solve, we have a negative 1 over cosecant square to the bottom. And however, we need to go back substitute, okay? Go back to look at it. We do not have a cosecant. We do have a cotangent y is x. So what do we need to do? We need to change cosecant to cotangent. See, cosecant square rolled into 1 plus cotangent square. Do you remember what that Pythagorean, right? The last Pythagorean, okay, as we learned from trigonometry. So here is a Pythagorean again. Pythagorean identity, okay. And the last step, of course, we directly see cotangent y is x. Cotangent y is x, so we back substitute successfully. Okay. Because cotangent y is x. So we find the final equation, the final formula, right? Okay, so we have 2 more left, which is the inverse secant and the inverse cosecant. Remember that? Okay, so let's look at the inverse secant. Inverse secant, we have a little bit complicated function. However, can you see we have an absolute value? Okay, so pay attention, which means what? The derivative is always positive, right? Can you look at it? Always positive. Of course, y always quite positive because the function is increasing. Why the function is increasing? Okay, of course, you need to go back to the definition. And in trigonometry, we do have 2 types of definition. Do you remember that? Okay, one type of definition, the function always we choose is increasing. And another is not always increasing. Some part, okay, one part increasing, one part decreasing. So more what? The derivative formula of secant, inverse secant depends on the definition. Can you see I put a remark here? And let me highlight. This is very important. Okay, the formula depends on the definition of the inverse secant function because we have 2 types of definition. Okay, so for our formula that I showed you here, so which definition we used? Can you see I use here? Our definition, we choose y is between 0 and pi. Okay, y does not equals to pi over 2. We choose this. Okay, if we choose this, the function is increasing always, so we have a positive. derivative, okay, the slope always goes up. Let me highlight it a little. So I said which definition we use. Okay, we use this definition. And so let me see. And the definition is here. And we get it. This is the definition we used. Okay. And if sometimes you find another derivative formula, which means if the formula is different from us, okay, and that formula we don't have absolute value, so pay attention. That definition for inverse secant is different from our definition, another definition, okay? And now, if we have the definition, everything is easy. What to do? We just take a derivative to both sides of this, right? Now, everything is the same. We take a derivative to these both sides, okay? Because we have an implicit equation. So here now is just the same. Okay, so we differentiate both sides. We differentiate both sides. Okay, and then see what do we get. We will get this. And the left take a derivative. Okay, what do we do is use chain rule, right? Use chain rule again, because y is a function of x. So here is the same as before. Okay, so let me put it here. We're going to use chain rule. We have to use chain rule. Okay, the right, of course, is 1. So chain rule is the outer times the derivative of the outer times the derivative of the inner. Derivative of the outer is what? Secant take derivative is secant times tangent. Can you see? Here is the outer, here the inner. Now what do? We solve the equation. We get the dy dx is 1 over secant times tangent. From, can you see, secant y equals x, we know. But tangent y equals what kind of x? We need to back substitute that we don't know. Okay, we do have a formula. Which formula? Okay, let me see here. And we can change tangent to secant. Therefore, we can back substitute to x. Okay, which formula? Link tangent to secant. Pythagorean, right? We used that. Okay, we used that before. Okay, so let me write it down. This Pythagorean is here. 1 plus tangent, the second type of Pythagorean you learned from trigonometry. Secant square y. Can you see? So tangent y is either positive or negative square root of secant square minus 1. Yeah, that's good. But why we have absolute value and why here we don't have a sign? Okay, all we need to do is look at the denominator at 1. And the denominator, I say denominator is always positive. Therefore, I have to put the absolute value. Okay, we need to make sure the denominator always positive. Okay, so all we need is because secant y times tangent y always positive. Y always positive. Let me look at where is y. Okay, y belongs to Q1 and Q2, right? Q1 or Q2, quadrant 1 or quadrant 2. Can you see? If y is in quadrant 1, both positive, so positive. If y in quadrant 2, both negative. Okay, secant negative, tangent also negative. Negative, negative makes it positive. So you see, okay, the denominator always positive. Therefore, we will make sure put the absolute value. And the last, of course, we back substitute. And because we have what? We have secant y is x, right? And if we plug back, and then we get the formula. Okay, so this is the formula for inverse secant. We have the last formula, which is inverse cosecant, right? Can you see the cofunction? Inverse cosecant. Okay, so everything is the same. Can you see? Here is all the same. and but we have a negative, so please pay attention to the negative, of course. And the formula depends on the definition. I still highlight this, okay, to make sure our formula use the definition is below. I'm going to show you, okay. If in the future you meet another formula which is different the definition, we use this formula. Can you see? Let me highlight this. We use the definition. Where is our definition? Okay, is here. Okay, so this is our definition, and our definition is for, can you see, for y belongs to negative pi over 2 to pi over 2, y does not equal 0. Okay, which means we pick a y belongs to quadrant 1 or quadrant 2, right? Okay, if we based on this definition, if you go back to trigonometry, draw a graph, you will find that the inverse secant always goes down, cosecant always goes down, which means the derivative always negative, okay, always negative. Now we're going to find why this is true. And the same, I think you know now everything is the same. We have an implicit equation, we do implicit differentiation, right? We differentiate both sides. Okay, we differentiate both sides and see what do we get. We will get this. Okay, take a derivative to the left, take a derivative to the right. To the right side is 1, of course. The left is the chain rule we have to use, right? Chain rule. Now here is the same chain rule. Okay, let me write. We have to use a chain rule to this, and then okay, the chain rule, which means the derivative of the outer negative cosecant times cotangent. Can you see? So here is where the negative comes from in the formula. Okay, comes from here, the inner and the right sides, and then we solve the equation. We get a negative 1 over cosecant. Now is the same way as the last we did. Okay, so we need to make cotangent to cosecant, so we can go back and substitute. So what do we get? And here, cotangent to cosecant, we do have a Pythagorean, right? We use the Pythagorean again. Which Pythagorean? This one. 1 plus cotangent square y equals cosecant square y. Okay, therefore cotangent y can go to square root of cosecant square minus 1. How about the sign, positive or negative? And the same, at the same, and we have this, and I will write here. We look at the denominator, cosecant y times cotangent y. I say it is always positive. That's the reason why I just put absolute value to make sure the denominator is positive. Let me write it down here. Cosecant y times cotangent y, always positive. Y, we look back to where is y. Y belongs to quadrant 1 and quadrant 2. Okay, or quadrant 2. If y belongs to quadrant 1, both positive, so this is positive. Quadrant, if it's quadrant 4, both negative, right? So this is still positive. Negative, negative goes to positive. Okay, so we have the last step. Of course, what is back substitute? Okay, use cosecant y equals x, right? And then plug back. We have the formula. So this is all the proofs. Okay, for this 6 type of trig, inverse trig functions. But a lot of formula, so we do have to memorize all these formula. Let me summarize, and I hope you memorize all these formulas. Okay, in the future it will benefit you much. I listed the left. Okay, is the basic 3 type. Inverse sine. Can you see that formula, right? Inverse tangent, inverse secant. all positive, right? And the cofunction, can you see, goes to cosine, cotangent, cosecant, all these inverse is negative. Okay, so, and other than this, all the same. Can you see, other than this negative and the positive part are always the same, which means if we memorize the left 3, we do know what is the right 3, right? Derivative formula. Let me highlight all you need to pay attention. Okay, so for this is we have a negative sign. Okay, for these 3 type of the inverse. Okay, if we for the cofunction, and that's all for this. And the last, we have 2 questions to practice together. Okay, simple questions. And the first, what to do? This time we do have a composite function, right? Okay, so we have to use a chain rule. This composite function, of course, we have to use a chain rule. All we need to do is just use chain rule. Okay, so let me get it. And therefore y take a derivative. Do you remember chain rule? Of course you remember. Okay, I'll put the dot here. So we have the derivative of the inner, the outer times derivative of the inner. Okay, so what is the inner function? U equals x squared. Therefore the outer function is inverse sine at u, right? Let me write. What is the derivative of the outer? The outer function is this at u. This is the outer function. Take a derivative. Do you remember we just get 1 over square root of 1 minus u squared, right? Okay, so we put this formula to here, and then we will get it. So 1 over what? Square root 1 minus u squared. What is u? U is x squared. So square of square, right? And what is the inner? The inner is, of course, the inner is x squared. Take a derivative. I wrote this one more step and then simplify, right? Okay, so 2x take a derivative. X with the second power take a derivative is 2x. I'll put the 2x on the top. Can you see? What do we have? We do have this. Okay, we do have this. The top is 2x. The bottom is this square root 1 minus x raised to the 4th power, right? Okay, so here are the first questions. Let us look at the one more. Okay, so here, one more question. And this question different is not a chain rule. The first step, at least. The first step is what? We look at is one function times another function, which means product rule. In these questions, what do? We have to use product rule. Okay, let me write here. So we have to use product rule first, at least. Okay, let me go into one by one. So what is the prime? Okay, is product rule is the first take a derivative and then the second take a derivative, right? Let me write the complete step. The first take a derivative. Okay, so this is the first, right? And then the second is the second function take a derivative. Okay, almost there. The first is this. I guess take a derivative is 1, which means arc. What is arctangent? Arctangent is inverse tangent. Okay, the same. Don't worry. Okay, it is the same. Is arctangent at square root of x, and then plus x times. Now we have to look at this term. How about this term? This term is what? Is a composite function. Okay, so pay attention. Now we have to use composite functions for this term. Composite function, which means chain rule, right? Which means chain rule. Okay, the inner function u is the square root of x. The outer is arctangent. Arctangent is what? Is inverse tangent. Let me write. So all we need to do is to find the derivative of the outer times the inner. Derivative of the outer. Let me see. The outer function is arctangent at u, right? Because u equals the square root of x is the inner. If I take a derivative, do you remember this formula we just get? Okay, is 1 over 1 plus u squared. Is that right? Okay, so that's the derivative of the out. I put it here. And see, per log in is 1 over what? 1 plus, of course, was u, square root of x. I may put square root of x and the square. See, this is the derivative of the outer, and then times the derivative of the inner. Square root of x is the inner. Take a derivative. You remember that formula is 1 over 2 times square root of x. Almost right. Now we simplify. See, we get everything. We simplify. Okay. So now I will get this. The first terms, they are the same. Arctangent at x plus. Okay, the second, can you see? Square root of x squared is x. So we have 1 plus x. And the 2 is on the bottom. But the x is on the top. Square root of x is on the denominator. Okay, we can cancel. Okay, divided out square root of x. Therefore, what do we get? The final. Okay, so we get a fraction. Can you see? And this is the fraction, so we get, and at the top is square root of x left. The bottom we have 2, and we have 1 plus x left. Okay, this is after the simplification. That's good. So here is all these questions, and that's all. Thank you. If you have questions for this topic, please leave your comments. If you like this video, you are very welcome to subscribe to my channel for more videos. In the next video, let's see. Okay, so we are going to deal with the derivative of logarithmic functions, and we will still use implicit differentiation. Okay, hope to see you next time. Thank you. Have a nice day. Bye.